So this hands-on will be the same as homework 0. We'll be trying to solve as many questions as we can, and then you have to complete the rest. And we're going to have 2 other hands-on that are going to be the same style. So that will be the participation grade. And I remember I told you homework 0 was optional, even though it counts as participation. So we'll be going for dropping the worst one, which is basically the one you don't submit. And participation is 10%, right? Is it 10%? Okay. So 10%, 3 hands-on, it means that each one is 3%. And you have 5 assignments for like 45. Yeah, so if you miss hands-on, you're basically missing 30 points from one of the assignments. So it's not much work, but it's going to have some effect on the final grade, so don't miss them. We have, what's that? Did you say we have to drop the participation lab? No, I just said that homework 0, we said it was optional. But these ones are not optional.
Oh, gotcha. So it's turning the hands on it.
Yeah. I created an assignment on Canvas. It's due on Wednesday. It shouldn't be too much work. And I'm giving you some hints for the homework 4, so that's good too. This is the second one. We said the first one was optional. So we still have 2 others, but we'll be counting in 3. So if you did homework 0, but you decided not to submit this one, it's fine. Okay. But if you missed homework 0, it means that you don't want to miss this. Yeah.
Will these be graded on correctness? Like we should aim to get every question fully correct by Wednesday, or more so by...
Yeah, I mean, we're not aiming for correct answers, but just we want to see that you understood what's happening and that you're following the logic of the notebook. You have some write-up questions. We don't expect to be right on point. Yeah, coding questions are straightforward. All right. So I'll try to give you 1 minute per question, and then we move forward to answering the questions. Okay. So we're starting with some simple data. It's a 2D data with labels -1 and 1. And we initialize our weights and the intercept. And we want to complete the linear plot. So to get the same plot that we're getting here, okay? I generated this one using the correct answer. So we just want something like this, okay? So this is we assume this is a SVM, and the straight line or the continuous line is the decision boundary, okay? And the dashed ones are the ones where the slack is equal to 0, basically, okay? So I assume this one is going to be +1, and this one is going to be -1. So basically here we have to write the equations for the three ones. I mean for the 3 lines. I'm going to start with the decision boundary, and you're going to do the rest, okay? So the equation is, I'm going to do this much simpler. So the decision boundary, we get Wx plus b equal to 0, okay? So this is W1 x1 plus W2 x2, okay? So this is what we call the y-axis. So this is actually our y, and this is our x, okay? I think you have seen this in homework 2, if I'm not mistaken. So the equation will be y will be equal to minus W1 x minus b. So this is plus divided by W2. Okay, so we're just going to code that one. So it's going to be W1 multiply x plot. Okay. And then we add the intercept. We divide by W2. We start the indexing from 0, so basically W1 here is. All right, I'm going to comment these, see what I get. Okay. I get this one. What about the other two? Any idea? What's the difference between the decision boundary and the two others? What's that?
It's what B is, right? It's just up or down.
Yeah. But what's the equation for the up and down, upper and the bottom lines? Okay. The difference here is okay. Decision boundary, the slack is 0. On the other two, we are getting 1 minus b. Sorry, in the other two, we're getting slack equals 0, which is different. Okay. So I'm just gonna write this here. We're gonna change basically the intercept. One of them we add 1, the other one we add minus 1. Okay. There we go. Okay, so we're done with that one. We're going to use it later, multiple times. Okay. All right, so we already have the weights and we have the bias. The question here, what's the margin? You can go back to the slides. You can find those expressions there. Any idea? Okay. That's one way to do it, but it's much simpler than that. Okay, that's the margin. And that's simply 1 over MP linalg, that norm squared. Well, say around 8, okay? You want me to zoom? Because of that one?
Yeah.
Okay.
Is that still the
Yep, that's the weight. All right, so based on this plot, which samples are considered the support vectors? Which one?
The bottom correct one.
Okay.
That like middle correct one.
Uh-huh. So do we count this one?
We need at least 3, right?
Not really. What do you think? Okay, so this zone or this domain is for the blue ones. The other one is for the red ones. So we have 3 points on the zero slacks. So do we have 3 support vectors or do we have 2? Two? Victory? Okay, yeah. So we only count the blue one because we are on the blue zone, I think the minus zone, and the other one for the positive labels. Okay? So here we have some points that have a slack, non-zero slack. In this case, this one, because it's out of its corresponding region. So in this case, we have 2 support vectors, not 3. And these are going to be -5, 0, and then 5, 2. Okay? -5, 0, and then we have 5, 2. Good. So now we go into the other question. I think I already give you a hint about it. Which train sample examples have non-zero slack? Support vectors?
They have 0 slack, the non-zero slack, you don't. Right?
Actually, support vectors should have slack 0, if I'm not mistaken, because they are on the 2 dashed lines. Okay?
So everything that's not that does it.
What's the expression of the slack?
The distance between themselves and that dotted line.
Yeah. I mean, mathematically. So in math, we just basically write W plus B which was it? WX plus B. And this one we multiply by Y. Okay. And this one should be equal to 1 minus the slack, which is going to be zeta here. I forgot which one. Yeah, zeta. No, not zeta. Psi. All right. So on the decision boundary, we're getting the slack equal to 0. I mean, on the dashed lines, we are getting the slack equal to 0. Because on the dashed lines, we get this equation. Okay? So we're going to have the red one here and the blue one here. Okay, because this one is outside its region, the other one is outside its region. Yeah, I'm basically answering 1.5. Okay, so I'm anticipating here. So the expression we have here is basically the one that we put here. And the point I'm talking about is going to be 6, 3, and minus 5, 1. Okay? So to compute these is straightforward. We're just going to put x dot W minus B. So this should give us that one. We're going to multiply by Y. Okay. And now we do 1 minus. And we can do MP clip. Or just do max. Oh, I'm getting 3. Okay. So I'm also getting the last one. I have this one. I have that one. Which is the third one. Okay. Also have 5. Yeah, I have 5, 5, 2. Oops. I have a problem here. I had to do plus. Okay. Yeah. Makes sense? If you use NumPy, there is a difference between maximum and max. The max will just give you the maximum value of the array, but maximum will give you the element-wise maximum of 2 arrays. Okay? We can check that our result is correct. I can do MP where is greater than 0. All right. Okay, this is more slides or course questions, so you have to go back to the equations to know what's the conditions that alpha should satisfy. So alpha is the solution of the dual problem of this SVM. And for this data, we have 8 samples, and we have like basically 3 choices of the possible solutions of the system. And we say that, well, there's some constant C for which we're going to have in the second and third option. We're going to write that there's some constant C for which is this true. And we're asking you which one is possible, basically. Any idea? So imagine the first 4 correspond to label +1, and the last, the first 4 correspond to label +1, and the last 5 correspond to label -1. So one thing in the slides that when we're solving the dual problem, we have one condition that says that the sum over I of alpha i's multiplied by yi equals to 0. Okay? So if you assume that the first 4 are +1 and the last 5 and the remaining ones are -1, well, you can discard the first one because we're just saying everything is a support vector. Means that all the points are just going to be on the 0 slack. does not make sense. I mean, it's possible, but the alpha 3, in this case, we have to sum the first two coefficients and minus the sum of the rest. It does not equals to 0, so we only have the option, the second option. Okay, second option, if we compute the sum, we're going to have c by 2 plus c minus c minus c by 2. Okay. For I, we're going to have c by 3 minus c by 2, which is minus c by 6, if I'm not mistaken. So this one is correct. Yeah, I'm too lazy to do the sum for the first one, but I'm sure it's not true. Okay? So we're going to move to part 2. We're going to start using scikit-learn SVM classifier. It's basically SVM. And we're going to try, first, we're going to start using the linear kernel. And we're going to start to play with the slacks coefficients before we move to the radial kernel. And once we do that, you'll be left with part 4. We would do some cross-validation plus grid search. If you're not familiar with grid search, just a method to look for the optimal or the best parameters of the model. It's pretty simple. I think we have seen something like that in homework 2 and 1. And the grid search is just a formal way to express the concept. So in this second set of data, we can already guess the support vectors somehow, depending on the slack coefficients, of course. But ultimately, I'm guessing this blue here and this red here, or the top, depending on the slack coefficient that we are going to choose. Okay. All right. So if you're following, you can go to. Okay, so the notation here is linear SVM, but it's actually the link is correct, but just the name is not. If you go documentation, it's the usual classifier. We have fit, predict, and all of those things, but we are interested in the attributes. Okay. So we get coefficients, which is W for us, intercept, which is B, support is going to be the indices of the support vectors. Okay. Support vectors are the values of the support vectors, so it's the data X indexed on support. In support is the number of support vectors, but we are also interested in the dual coefficients. Okay. So this is the tricky part. Even though it says the dual coefficient, it does not return alpha. It returns alpha multiplied by y. Okay? Because we know the dual coefficients are going to always be greater than 0. But in this case, it's going to give you like, I don't know, like -1, 1 here, or something like that, or 0, 2.5. Because it multiplies by the labels. So it's going to save you some work there. Okay? Yeah, let's start. We're going to use 2 arguments. We're going to use the C argument for the slack coefficients, and then the kernel. If you go to documentation, you can choose between linear, polynomial, radial, sigmoid. Precomputed is you provide the matrix K. Okay? You compute your own matrix K and then you provide it. It also works. For polynomial, you get to specify the degree. For the radial, you get to specify gamma. Okay? But for polynomial, we have degree and we also have coefficient 0. Okay. So for polynomial, if you have A and B, it's going to be C plus A scalar B to the power of P. Okay. So P is the degree and C is the coefficient 0. Okay. For the radial, which is noted RBF, AB is going to be exponential minus the norm of A minus B squared divided, I'm not sure if it was gamma squared or gamma, but I like to think it's gamma squared. All right, yeah, let's get started. Let's use this. We have 15 minutes left. We're going to try to finish part 2 and 3 and give you the easy part, which is part 4. So I'm going to call it SVM equal SVC. We're going to use C equal 1, and then I'm going to use kernel linear in this case. Yeah, let's use linear. Okay, so I'm going to fit the data, fit the model using X and Y, and then I'm going to define W, which is SVM coef. Yep, I think it's correct, and then here's going to be intercept. Oops, and underscore, okay. All right, so we have a shape problem here. Let's look at the shape of W here. Yeah, it's 1, 2. Okay, we're just gonna use the first. There you go. This is what I get for coefficient 1. We're going to play with C later, but let's start identifying the support vectors, okay? So we said we're going to do svm.support to get the indices. Okay, we have 8 of them. So I'm going to call this sup index. And let's get the alphas. It's going to be svm dot dual coef. Not sure if it's plural or not. Yep. Okay, so as you see here, we're getting the negative values on alpha. That's because we multiply by the labels. Okay, and we can check that this is true by looking at y support index. There you go. Yeah. So the first 4 are negative label, and the last 4 are positive label, and they have the same sign as the alpha. So the alphas here are already multiplied by the labels. Okay? So I'm going to call this alpha. And now that we have alpha, we know already what the support vectors are. We're going to do something that you already asked to do in the homework, which is we want to compute the intercept and compare it with the intercept we get from the SVM. Okay? Is anyone trying to code it, or are you just thinking? Okay. So alpha there is actually alpha y in the equation. That's basically what I was explaining before. And the kernel is linear. It's the linear kernel, so it's just the scalar in this case. And we sum in over S. S is the support index. Okay, so let's do this. First, I'll start with this quantity here. Okay. So my matrix K is the linear kernel. It's going to be X indexed on support vector. So I'm only interested in the support indices. I'm going to do dot. I'm going to do the same thing here. I'm going to transpose. Okay. And you can check that this is basically the same matrix of the linear kernel later. All right, so now I have K. I want to multiply by the alpha i's, which are stored in alpha. So in this equation, I'm taking this matrix K of the kernel value between the support vectors, and I'm multiplying each row by the corresponding alpha I. Okay? So this one has 8 elements. In this case, this is going to be an 8 by 8 matrix. So I'm going to multiply the rows of this matrix. Okay? So in this case, it's going to be alpha multiply K. Okay? So now I have this matrix here, but now I'm summing the rows once I'm multiplying them. So I'm going to do sum over 0. So now I have this quantity here for each m. Okay? Now I'm going to the labels, but I'm only interested on the in the labels of the index of the support vectors. I'm going to do sub index. So I'm getting 8 values in this case. Oops. And now I'm going to take the average, okay? Because I'm summing over the elements of the support vector set. So I'm just going to do mean. All right. So this is my intercept. Oops, I'll call it intercept. Now, because I changed the data, so let me just go back. And, yep, I was here. I want to compare this to the W we have that we found, okay? Sorry, the intercept. All right, so there is some gap there. So we are getting 3.33, and the intercept by SVS is 3.39. You might think, well, it's not much, it's just 0.05, but nah, it makes a lot of difference. We're solving things on a float 32. That's a huge gap. Okay? So what happens here is that in the formulation we have in the homework, let's look at the linear kernel. So forget about the radial or the polynomial, just to get an understanding of what's happening here. So what happens during the prediction is that we are getting W equal the sine of the alpha i's yi. Let me go. And now I turn it off, but let me try. Okay, I turned it wrong. Okay. So here I'm getting the sine of the sum of alpha I wi, k between, in this case, I'm using the linear kernel, so it's going to be xi x plus b. Okay, so at the support vectors, we assume that the slack is 0. So in this case, y is going to be 1. Okay? Sorry. This one is going to be y, either +1 or -1 on the support vectors. Okay? So what happens here is this is basically, I'm going to write w equals, so when I say xi, these are the training data. I'm summing over the training data, or basically x train, all right? So w in this case is the sum of alpha I, yi, xi. And this equation you see here, it becomes wx plus b equals y, okay? So in that expression, what we're saying is that we're saying that this is true for all support vectors, okay? So if I sum over xi belongs to S, minus y, this is 0. And now I'm going to average over the size of S. I'm going to take b to the other side. So b is going to be the average over the size of S. Sum of xy belongs to S of wx. Sorry, 1y minus wx. Okay? But what SVS does, it does not do that. It does the minimum over xy belongs to S of y minus wx. So we are taking the average, but in SVS we take the minimum. So let's take the minimum and see what we get. So here I'm just going to take the mean, the minimum. Whoops. So I'm doing y support minus, nope, I'm not interested in this. Okay, so I'm doing an alpha k. The prediction would be some 0. Well, let's do it the other way around. Just gonna do this, okay? Okay, I'm missing something here. K is good. Something is off here. Let me see. Let me do it the other way around. Let me do W support index. So I'm basically doing y minus wx of the support vectors, okay? Minus x of support index. Gonna do dot w. And let's take the minimum. Let me go ahead, I run this model, SVM. Okay, I had the problem because I initialized the data. This is min, this is max, this is mean. Doing W minus WX. Should I multiply by the sinus also? 1 second. Yeah, I'm missing some minus somewhere, but basically the minimum, but I'm multiplying by y. In this case, I'm basically have to go the other way around. Y support index. And here is the max. Okay. Yeah, something is off. I'm missing some sign somewhere. And okay, we don't have time for that. I can check it later. But you get the idea. We're taking the average in this case, but in SVS, they take the minimum. Okay. Now, in the remaining questions, we try to play with C. We try different values. You're just going to use the same code that we have here. Just going to change like for 1, 2, 3, 4. So I'm going to try like with 1. I'm going to try here with 10. Yeah. So you see here that the larger the value, the less overfitting we get. The smaller the value, the more overfitting we get. Yeah, so here we ask you about the bias and variance, which is basically the overfitting, underfitting thing. Now in nonlinear SVM, we're going to play now with the kernel parameter. So far we did the kernel is linear, but you can do RBF or you can use polynomial. So in this case, I'm going to just do the same thing, but here I'm going to do linear. I'm going to do RBF. Okay. And you can play with gamma as you wish. So I'm just going to start with the initial 1, and we don't have to. So in nonlinear plot, you don't provide W and B, you provide SVM. Because in nonlinear, we don't have weights. Okay. Yeah, we don't have weights, so this coefficient thing does not make sense in the nonlinear way. This is using the default value of gamma. Let's try gamma equal 10. I get something like that. So then you can do some analysis.